What's up, guys? Welcome back to another training video, and today what we're going to do is talk about oil return, why it's important, but eventually the meat and potatoes of this is to get to the oil failure control, what it's there for, how it works, and how it helps protect the compressor if there's an oil return issue with the system. So we're going to talk about a few things here first before we get into oil failure controls. So most of us here, we're technicians, we're not engineers, we're not designing the system. But some considerations that need to be taken is equipment sizing, pipe sizing, and refrigerant velocity. So if we have the equipment size correctly, the piping size correctly, we will have the refrigerant velocity needed, in most cases, to get our oil to flow through the system from compressor through the entire system back to compressor. So we keep that oil level flowing through that system and we keep the compressor lubricated. Another important factor of oil return is using traps. Now, I've drawn out two different diagrams here, two different scenarios really is what it is. And this one here is more of like if you've ever worked in a server room or data center, this is an application you might see with the compressor, the coil, the metering device all in a package unit down here with the condenser up on the roof. And this is more of like a condensing unit on the roof with an air handler down here with the evaporator, blower, and metering device right there. So on a riser like this, when we're going up and down, it's called a riser in piping, we want to trap it at the very bottom. Now, I suggest you read the manufacturer's specifications on this because they all could be different. I've seen anywhere from 10 feet to 20 feet. Every 10 or 20 feet, you have to put a trap there in order to collect that oil. But at the very bottom, I've always gotten to the habit of putting a trap at the bottom of the riser before we continue to go up. What this does is it traps, essentially, the name is really what it is. It traps the oil in here. So on the off cycle, it doesn't just hang out in here somewhere if the piping is kind of all over the place. So when the compressor starts up, this trapped oil will move its way up to the condenser, all right? Now, this trap here, this is called an inverted trap. That is really, really important, and I'll tell you why. Because on the off cycle, if this was just a straight piece of pipe, what could happen is all the oil that's in here could actually start to drain back down, and we have to start this process all over again. So this inverted trap keeps the oil in the condenser, so it doesn't fall back down. So when the compressor goes to start up, the oil that's trapped in here now because of this inverted trap will make its way back down through the rest of the system and back to the compressor very, very easily. So that is a way you can trap a system. Trap at the bottom and an inverted trap at the top. Now, if this was like a 100-foot run or something like that, you might see traps going up every 10 to 20 feet, depending on the manufacturer's specifications. And the reason for that is if we come up to 20 feet here, and we trap it, we are trapping that oil there. So every time the compressor starts up, that velocity from the discharge line moves the oil back up to the next trap, and then we keep elevating the oil to the condenser and then back through. So that's why traps are super important in this sort of scenario. The other scenario here is I've drawn a condensing unit on a roof and an air handler down inside. So obviously we are going to leave the condensing unit. We're going to drop down. The liquid line is going to come in through the metering device evaporator. And the evaporator, there's a riser back up. At the bottom again, I have trapped that. Okay, so we want to trap that oil right there. So we're not logging the evaporator. It's not running back and logging in the evaporator right here. We want to keep it trapped in here. So when that compressor starts up, that velocity is going to take the oil that's in the trap and move it back up to the compressor right here. Now, on a style like this, I haven't seen a lot of inverted traps, but it's not a bad idea to do so. But the problem is that a condensing unit such as this, where the piping comes down at the bottom, if the piping enters at the bottom, in order for an inverted trap to work, you really have to come up past the height of the condenser, right? And then go back in. That's why I've drawn it here, above the height of the condenser, right? Because if you have it down lower than the condenser, that oil can still get back. But if it's up, it's not going to lift and go back down. So that's why I've drawn it like that on this particular style, but always keep in mind to trap it at the bottom, especially reading the manufacturer's specifications. Now, on a system like this, I've also seen it where they have put in a double riser, right? And what a double riser is if this compressor, let's say it could run at a variable speed or it can unload because the load is changing inside the room and the pressure is dropping down lower than normal because of the variable load. If it doesn't have enough velocity to get up this pipe, what I've seen in the past is a double riser where another smaller suction line will come off of this. It will be trapped and move up to the condensing unit. Now that smaller line is going to have more velocity. That velocity is what's going to take the oil back to that condensing unit. Okay, so now we have to take what we've learned here, all right, with oil return and apply it to a semi-hermetic compressor and see why this is so important. Now, drawing a semi-hermetic compressor, the internals, is not that easy. So I've done my best here standing with this whiteboard with markers. We have enough here to show you exactly how an oil pump works in this compressor. So when the oil comes back, it collects in the sump. This is the sump, and there'd be a sight glass here so you can visually look at the oil level. Now on the side here, there's an oil pump. What happens is the oil is pulled from the sump by the oil pump up here, okay, and the oil pump discharges it through the crankshaft here and lubricates all the parts of the compressor. Now you can see why, if there's a lack of oil return getting to the sump, we're going to have an issue with our compressor because we're not going to have lubrication through here. All right, so there's a device called an oil failure control that we put onto this compressor to let us know that, hey, we don't have enough oil. There's either a lack of oil because of oil return or the oil pump has malfunctioned and we don't have any oil moving through that compressor to lubricate it. So let's go on to the actual oil failure control. But you guys just got to know, the oil comes back to the compressor, is stored in the sump. The oil pump grabs it and pumps it through the system. This is the sump, guys. This is the discharge of the oil pump, and there's a differential pressure between the two. Okay, this pressure here in the sump is different from the discharge pressure of the pump that's moving the oil through the compressor. All right, the video's been leading up to this point. This is our oil pressure control. Here's the part number for it, very basic control. Here is our compressor right here. Here's the sump of the compressor, and our oil pump lives here. We have the discharge that feeds through the crank shaft of the compressor, and this is teed off so we can read the discharge pressure of the oil. So we're going to take a cap line, tie in the sump to the controller. We're going to take a cap line and tie in the discharge of the oil pump to the controller. So there's a couple of circuits we need to talk about on the control itself. This one here has a heater in it, which starts a time delay, which is tied in with this contact right here. This contact right here is controlled by the pressure differential. Okay, and I'll get into that in a minute. This circuit right here is your control circuit, essentially. So this can be tied in with like your head pressure control, your low pressure control. So we have a circuit here and a circuit here. So the way this works is let's say we have a predetermined set point in here. Let's say that set point is 5 psi. Basically what we want to see is 5 psi difference between these 2 points, just for an example. All right, so if this was 55 psi here, we would want to see 60 psi here to give us that 5 psi differential. So when the compressor starts up, this oil is going to be drawn into the pump, moved across the crankshaft, but we're teeing off to get the pressure here. So we want 5 psi differential. All right, while that 5 psi is building, our compressor is going to run. Okay, and there's a time delay circuit here that if we do not build enough pressure in time, our compressor will shut down. So while our compressor is ramping up, is starting to run, this circuit here comes into play when the contactor closes. The contactor closes, the compressor is running, power to the heater. That heater starts the time delay sequence. Okay, if we don't get to 3 psi above set point. This literature is pulled right from the manual, by the way, of this. If we don't get to 3 psi above set point, this will stay closed. If that stays closed, the heater stays in the circuit. If the heater stays in the circuit long enough for the time delay to activate, this will open our safety circuit and the compressor will shut down on oil failure. All right? If the compressor's already running, let's say we go through this. Let's say the compressor starts. We send power through here. The heater starts up. Our time delay is activated. Okay? But let's say we get 3 psi above set point. This will open. This will now open up. This is a pressure activated contact. This will open. The heater will be taken out of the circuit. This time delay contact will never ever open because this heater is now out of the circuit, and the heater is what activates the time delay, almost like a sequencer, if you guys have ever seen a sequencer. If this doesn't open, the compressor continues to run. So now we're happy, we're running. But let's say there is an issue with oil down the line. Let's say we have an issue with oil return coming back to the compressor. We don't have enough oil in the sump, or we have an issue with the oil pump, like maybe there's something clogged and we can't build up that pressure that we need, right? What's going to happen, here's the other rule that's from the literature, this will close when the delta P drops below set point. So we said 5 psi set point as an example. So let's say we hit 4 psi. This is going to close again. What that does is it brings the heater back into the circuit. Now that the heater's back in the circuit, we're going to initiate the time delay. After that time delay is over, this will open, cutting the safety circuit, shutting down the compressor. Now, there's usually a reset on these, manual reset. A lot of techs, they'll come up, they'll reset it, everything will be fine. A couple days later, it will trip again. Okay, and I've seen too many techs go out and replace these things because they think the controller is bad, but 99% of the time, guys, it's an oil issue. Okay, it's either an oil return issue or it's a problem with the oil pump itself. So we need to figure out what's going on. So in summary, our equipment needs to be sized properly. Our piping needs to be sized properly to get the velocity we need through the system. If we don't have that velocity, we're not going to have the oil return. Traps are important. Inverted traps are important. Okay, the controller itself works in conjunction with the differential pressure between the sump and the oil pump discharge. Okay, we tie these both into the controller through cap lines. We have a couple of circuits here. This one gets powered when the compressor contactor pulls in. Okay, and then we engage this heater. Okay, this one here is a control circuit tied in with the safeties like high pressure, low pressure, so on and so forth. Compressor starts. All right, we start to build pressure. If we build pressure 3 psi above set point before the time delay is over, heater is taken out of the circuit, time delay contact stays closed, and we continue to run. All right. If it doesn't build pressure 3 psi above set point, guess what? This stays in the circuit. This opens up. Compressor shuts down. The compressor is running smoothly for a couple of hours, and this closes because we've dropped below the set point, the 5 psi set point. Guess what? This closes. Heater's back in the circuit. We initiate the time delay again. This will eventually open, cutting compressor operation. And when that happens, guys, we need to look into why we have an oil return issue. Okay, that's it in a nutshell, guys. Oil failure switches, a little bit on oil return and how the pump works. Happy HVACing.